Hi, it's Sunnygun from River Hill High School. This video is my Physics 1 fan project, and as you can see from the title, it will be about gravitational force. First of all, let's start this with a little fun question. Now, imagine there's an apple here and I want you to weigh it for me. What device should I use? Well, you might think of these two devices that we normally use in physics labs. And here comes the question. Should I weigh the apple with a scale? Or should I weigh it with a balance? At this time, you might say, well, it's the same. There's no difference between using a scale or using a balance. But not quite. Let's try measuring the apple with both of them. We put the apple on one side of the balance and we put the weights on the other side. And it gives us a result of 0.25 kilograms. And then we use the scale to weigh the same apple. And it also gives us the same result of 0.25 kilograms. You're probably gonna say, oh, they both show 0.25 kilograms. They're both gonna give the same answer, then what's the difference? So, does that mean we can use either of them? How about this? Let's change the location a little bit. So we take that apple and these devices with us and travel to the moon.
5, 4, 3, 2, 1.
So now we are on the moon, which has a weaker gravitational force on the Earth. And we do all these procedures we did before. We place the apple and the weights on the balance again and get the same result of 0.25 kilograms. But this time, when we put the apple on the scale, what we get is only 0.04 kilograms. So how does this happen? To understand this, we need to first distinguish between the concepts of weight and mass. In other words, what is mass and what is weight? By definition, mass is the measure of the amount of matter that an object possesses, which include these small components of an atom, for example, protons, neutrons, and electrons. And we measure mass in SI unit kilograms or kg. But weight, on the other hand, is defined as the amount of force exerted by gravity on an object, or in this case, the amount of force exerted by the gravitational field of either the moon or the Earth on the apple. In SI units, it is measured in Newton or N. This basically explains why we got different answers. When we use the balance to measure the apple, what we really got is its mass. Think of it, the gravitational force acts on the apple and the weights on both sides of the balance are the same. The amount of substance in the apple remains the same no matter we are on the Earth or on the moon. So we got the same answer. And we will get the same answer again and again in other planets with all different gravitational fields. But when we use the scale, it gives us the weight of the apple. When we place the apple with the mass in the gravitational field and let it free fall, it accelerates to the center of the planet. But when it is placed on a scale, it stops accelerating. This indicates that the scale exerts a force same in magnitude with the gravitational force but in opposite directions. It's called the normal force, and this is the weight that the scale measures. Weight, also called the gravitational force, is dependent not only on the mass of the object, but also the gravitational field strength of the planet it is on. When the gravitational field strength changes, the gravitational force changes too. Here comes the formula of it. F equals to m times g, which comes from the formula F equals m times a. And here, F stands for weight or the gravitational force in Newton. M stands for the mass of the measured objects in kilograms. G stands for the gravitational field strength in Newton per kilogram. As we all know that G moon is slower than G earth, and M of the apple remains the same. F moon must be less than F earth. This is the reason why the scale on the moon reads a lower value than that on the earth. And to add on, I think these units should be in Newton, not kilograms, where we are measuring the gravitational force of the apple. Wait, let's look back. How do we know that G moon is lower than G earth? To do the actual comparison, we should first find G moon and G earth numerically. Here's the formula we need. So we get Fg equals to big G times big M times small m over r squared. G, or gravitational constant, equals to 0.0743 times 10 to the negative 11. The small m stands for the mass of the object, and the big M stands for the mass of the planet, and they are all measured in kilograms. And r stands for the radius of the planet. By the way, we assume that all the measurements were done on the exactly surface of each planet. Now we plug Fg equals to mg into the formula. We take away the small m and we get G equals to the big G times the big M over r squared. With this formula derived, we can now calculate G moon and G earth respectively. Given that M moon equals to 7.36 times 10 to the 22 kilograms and R moon equals to 1.74 times 10 to the 6 meters, we can calculate G moon using the big G times M moon over R moon square. We plug in the numbers and we get the result of approximately 1.62 meters per second square. Then we use the same method to calculate G earth. Given that M earth equals to 5.97 times 10 to the 24 kilograms and R earth equals to 6.38 times 10 to the 6 meters. Again, we use that formula, G equals to the big G times M over R square. We plug in the numbers and we get the result of 9.8 meters per second square. By comparing the two results, we can conclude that G moon is smaller than G earth. Now, we have this information. We can calculate the weight or the gravitational force of the 0.25 kilograms apple on moon, given that G earth equals to 9.80 meters per second square, and G moon equals to 1.62 meters per second square, and M of the apple equals to 0.25 kilograms. And we write F moon equals to mg moon equals to 0.25 times 1.62, which gives us 0.405 Newton. Let's go back to that scale on moon. We have F moon, and we can use it to estimate the value that the scale will give. We use F equals to mg earth, and we plug in the numbers, and we get the new M of 0.04 kilograms, which exactly matches the value we got previously. Thanks for watching, and I hope that was helpful.